Hello, everyone, and thank you for joining us today for the webinar on using Radiant Vision Systems solutions for backlit components when characterizing light, color, or defect analyses. We appreciate you taking the time to be here. My name is Matt Schulze, and my colleague Chris Williamson and I will have the pleasure of taking you through today's material. Today's webinar will be in a slightly different format, and we'll see a bit more conversational than our traditional webinars from Radiant.
So to introduce Matt to the audience, Matt Schulze leads Radiant's global automotive business strategy and has over 10 years of experience in automotive metrology, working across tiered suppliers and OEMs. Matt has led projects at all levels of the supply chain, coordinating cross-departmental teams to ensure customer success and guiding new solutions development at Radiant to address specific industry challenges.
Thanks, Chris. And of course, Chris Williamson's a sales engineer at Radiant. Chris supports our international customers at Radiant, where he's worked across multiple applications and product groups to implement display and lighting solutions. Chris has traveled pretty extensively to meet with different engineers at their facilities and work in different markets to directly understand and apply in-depth product knowledge to really adapt the Radiant suite of technologies for specific projects. Before we begin, I'd like to go over the Q&A, which will follow the presentation. Our presentation today will last approximately 30 minutes, in which during this time, you're welcome to type in any questions that you might have as we go through the webinar. You'll be able to submit questions in the window in the GoToWebinar interface, which is located on the right-hand side of your screen. Questions will be queued and answered by Chris or myself following the presentation, so feel free to ask questions at any point in time. If we don't get to all of your questions, we will look to follow up with you after the meeting itself. So Chris, why don't you introduce Radiant to the audience?
Thank you, Matt. So to give a brief introduction to Radiant Vision Systems, we're a world leader in light and color measurement, and we've been providing scientific grade measurement solutions for over 20 years. Matt and I are excited today to share Radiant's expertise in light and color measurement and talk about a brand new solution that we offer that combines the best of photometry with machine vision for inspecting backlit icons and shapes. Matt, could you go over the agenda?
Yeah, I'd be happy to go over the agenda. So today's agenda is pretty exciting. We're going to talk about backlit icons, shapes, and text. So basically breaking down the trends and inspection considerations we see for these types of applications. We'll go through the current methods that exist today in the industry, whether that's using multiple systems, the issues we see with imprecise registration of these unique shapes that are on backlit emitters, and of course, one of the bigger issues, which is zero tolerance for variable measurement conditions. Then we'll step into the benefits of the new solution that Radiant's offering, which is the VIP software. We'll talk about photometry and dimensional quality in one precise solution. We'll go over responsive registration of the unique shapes that we're looking to characterize and talk about how easy it is to really implement our solution, whether you're talking about end of line or the use in a lab. And finally, Chris and I will step through a software demonstration to really show you what the platform looks like, how you would set it up, and what your final results might be. So we'll start off by giving a brief introduction to backlit icons, shapes, and text and the criteria we usually use to inspect for these applications.
So Matt, in this example here, we see this from an automotive application, but are there applications outside of the automotive industry?
Yeah, of course, Chris. There are definitely more applications outside of automotive. We see similar requirements in electronics, both, of course, in the interior, exterior of the vehicle, but more importantly, we see consumer electronics, avionics, medical devices, general appliances, and much more. All of these components actually have a laser etched aspect to them, which traditionally have been inspected either with vision systems or human inspection. And today we're really going to talk about bringing this concept into our core technology of imaging photometry.
So what it seems like, for instance, in the past, looking at this example of an instrument cluster, we've been able to look at the luminance and color of each of these backlit components. For example, we'd be able to determine that this character is too dim and this character is too pink and is a different color. But now we can also look at defects, misalignments, and other laser etched inaccuracies. For example, in this number, there's an etched component missing, and this check engine light has an obvious defect in it.
Yeah, that's correct. And we'll look at some more examples throughout this presentation, but I'm hoping it'll become really obvious to the audience what we're bringing as a vision analysis addition to looking at lit components within different industries.
Now, I'd like to break down the two major components that we would look at when evaluating instrument cluster. First, we need accurate and repeatable measurements of the photometric properties of the icon, including brightness and color, to check if they are meeting specifications. And even beyond this, we need to look at the uniformity, both within a character to make sure it's sufficiently and uniformly illuminated, and also from one character to another to ensure that the brightness and color is consistent with other icons. Second, there's also the need to ensure that there are no defects in the character, whether that's an inclusion, exclusion, deformation, rotation, warping, or some sort of incorrect position. Really, what inspection is needed is the icon complete and whole? Are defects present in the etch or overlay? Is the icon in the correct location and orientation on the device? Now, Matt, from your experience, where do these type of defects usually come from?
Yeah, so we see most of the defects really coming through the laser etching process. And although laser etching technology has advanced quite significantly over the past couple of decades, we still often see issues with program loadouts or component placement. And this generally leads to issues that you mentioned, like inclusions, text rotation, improper font sizes, different dimensionality, and much more that need to be taken into consideration. And what I really like about what you mentioned, Chris, is we're looking to break down that there are two fundamental criteria for inspection, the photometry side and the visual inspection side.
Yeah, what we're talking about is a solution that brings everything together to make our inspection process very efficient. We want to combine photometry and dimensional inspection for a complete analysis, which is more effective because when we only need a single system to do it, this would also make the inspections very quick, especially if we can add benefits for minimizing downtime between inspections.
Now, generally speaking, do we feel that there's really many other instruments or devices currently in the market that can do this?
No, there really isn't. Radiant has strived to bring a novel approach to this level of inspection.
Okay, so to talk about combining these two measurement components into a single solution, some of the examples we see in various markets are blind zone indicators for exterior mirrors, as an example. These tend to be in a market where further analysis, absolute quantification, various components or standards need to be applied, whether these are global standards for quality or for safety. We have experience working with various committees, whether it be the SAE, the MIL, or ISO standards that have really been applied to such applications on a global basis. Now, of course, these aren't the only applications or the only standards working bodies we work with, but I hope that we can talk about a little more of these throughout this presentation. Now, let's take a look at what problems we see with the current methods where we're splitting these technologies out separately and why manufacturing engineers may dislike multiple components to achieve a final analysis. Chris, why don't you take us through the different position areas and sections?
Yeah, absolutely. The first problem is that really in many cases, multiple systems are required for complete evaluation. So for example, when using a spot-based photometer like we see here, the light and color accuracy is great. But to measure multiple points on the character requires either multiple systems measuring at the same time or a single system moving to different locations on the part and taking measurements. You could imagine the complexity this brings when measuring many backlit icons in a single field of view, let alone just one. We can also not inspect for defects. So while this method solves the issue of accurate and repeatable photometric measurements, it is clearly not efficient and does not have the added advantage of inspecting for defects. Another option is to use a traditional imaging photometer or colorimeter, something that Radiant has been providing for years. In this case, we can calibrate the photometric measurement to obtain accurate and repeatable results. And with the 2D imaging capabilities that we offer, we can measure multiple locations and multiple samples simultaneously, which makes the acquisitions effective. But this option has traditionally left out the key requirement of defect analysis. And finally, what most people are familiar with are machine vision cameras, which are efficient and meet the requirement for finding defects. However, these are not photometrically calibrated and cannot acquire and characterize absolute photometric values for light and color.
Okay, so if I understand things correctly, with the traditional methods, you'd be required to use two separate devices, something like an imaging photometer and, of course, a machine vision camera to really properly analyze your device and understand all your testing requirements against the component you're evaluating.
Yes, that's absolutely right.
Okay, and to look at that in more depth, you'd have added costs, of course, more complexity with multiple softwares and integration, while obviously needing to consider the added tack time with multiple devices operating on the same line. Now, Chris, in my experience working with photometry equipment, I've often heard that registration, I personally have seen that registration can be quite difficult using basic metrology softwares. I know even looking at Radiant's previous softwares or our parent company or sister companies, generally registration has not been overly robust, and the industries are looking for something that it allows us to register on more complex shapes or products. And this generally has required one-off developments in the past.
Yeah, it certainly can be a challenge. So now let's take a look at the second major problem we see with current industry methods to really understand why a more advanced inspection software is needed. So here's an example where we are measuring a standard rectangular region of a display. This is from Radiant Vision Systems Register Active Display Area, or RADA, which is from our display inspection solution, if you're familiar with that. In this case, the registration requires 4 illuminated corners. Once the display has been cropped to the emitting area, we are able to analyze the display for various characteristics. In this particular example, we just see an analysis on luminance and general uniformity, but of course we can analyze other properties as well.
Okay, so Chris, if we're not looking at traditional displays though, and we're looking at laser etched overlaid products in either the aerospace, medical or consumer, maybe even auto industry, we really would need a different type of registration method because each icon that we see here has a unique shape, a size, a rotation, or defined analysis region. This really results in requiring a more precise method than what you just spoke about.
Yeah, that's really it. Traditional methods where you define the measurement area using a standard shape that does not match the exact contour of the illuminated area, you run into these issues. So looking at this example, with traditional thresholding, we can't pick up the unique shape of the icon to determine if there are any abnormalities in the part. The other thing is that traditional thresholding doesn't account for the placement of points of interest relative to an icon's rotation. In other words, the point of interest are not correctly placed relative to the emitting area. So, Matt, this leads us into another problem where the methods we just looked at don't have tolerances for real-world production level measurement conditions.
Yeah, that makes complete sense because from my experience working in the industry, customers have often stressed their concern for metrology systems and the level of registration compared to machine vision or the very high levels of fixturing that generally would be required. When looking at my own customer base and working with several different integrators, I know that this has been a challenge and a frustration for many. And speaking to that challenge, the following really are some examples of things that I know are problematic for the large customer base at hand. When measuring components and any level of rotation or position change is applied, you often end up with your analysis regions, or in this case, your POI, being placed outside the desired icon or location within the field of view. And when looking at multiple icons or components, this leads to further levels of complexity as a single etched area could be problematic and throw off the entire analysis process, which leads to failed components regardless of the parts, whether the part's properly illuminated or uniform at the end of the day. So Chris, we've identified the problems and what previous technologies have offered. What are we doing at Radiant to define a solution?
Yeah, that's a really important question. What Radiant has defined is a new software module to add on to our existing test software to rectify all of the issues that we have talked about that exist in the market. This new module is what we're calling VIP, which stands for Vision Inspection Pack. Radiant's VIP software solution combines an imaging colorimeter or photometer for accurate and efficient photometric measurement with automated visual inspection software featuring the VIP license for registration and defect detection of unique backlit areas.
Okay, so what Radiant's really offering to our customer base is the following, right? A single camera platform with various resolutions based on application needs, the ease of registration for flexible and complex applications against the DUT, providing absolute photometric analysis for light, color, and all aspects, of course, derived of them. And then finally, the added value for defect detection for inclusions, exclusions, position, dimensionality, and much more. To continue on that point, for the photometric analysis side, setting tolerances for defined limits on luminance, color has never really been easier. Pass-fail analyses can be applied to each aspect of the measurement sequence, allowing the users to truly quantify the entire emitting character or selecting defined regions of the POI placement as seen in this slide and information logged down in the table below.
And here's an example of applying a little bit more of that. One of the nice things is that a user can pass or fail the color of a point based on where it falls on the CIE chart and whether it is within a user-defined shape on the chart. This could be an ellipse, a rectangle, polygon, really depending on how the specification is written. You can also apply different pass-fail criteria for icons of different color and brightness, as we can see in this example.
So really, here to start, we see examples where our VIP software becomes advantageous when looking at laser etch defects. We've discussed, inclusions, exclusions. Icons on backlit components are often produced by laser etching shapes and text into various substrate layers, and then combining these layers with plastic overlays and filters. If the etching process is done inaccurately, icons may exhibit defects such as inclusions or exclusions of the substrate, which manifest as dark areas, missing areas, or inaccurate contours against the backlit icon themselves. Now, knowing that the registration is critically important, why don't you explain what the registration routine looks like in our software, Chris?
Yeah, let me give a high-level overview of what is really happening in the software. So first, we will use a golden sample to create a model that subsequent measurements will be located and compared against. The software will use thresholding to define the exact shape and contours of the golden sample. This model is stored in software so that later measurements can be properly aligned relative to the location of the golden sample. And then each new measurement is compared to the model. Then the software will, of course, inspect for defects relative to the stored registration.
So this shows that we're bringing intuitive machine vision registration and analysis into a photometrically calibrated piece of equipment and applications. I really like the high-level example we're showing here and the idea of defined examples against a golden component. The software registration that we're offering in VIP really removes the need for complex fixturing and offers a robust and intuitive way to handle your application. These slides show a great way of space manipulation and dimensional translation of the parts within the field of view, yet the POIs are still properly aligned and placed.
The software also has a good amount of flexibility to register samples either locally or globally. Now, what I mean by this is that locally you can accurately measure each area of interest even if it is rotated or translated. So in this case, you could place multiple samples in the field of view and the parts can be misaligned relative to one another, and you can still correctly inspect the part. Globally, you can check for accuracies, inaccuracies, or accuracies such as position, shape, size, relative to one icon, from one icon to another. So here's an example where we see multiple samples placed in the field of view, and they shift position and rotation relative to one another, but they're still successfully registered and the points of interest are correctly placed in the position that we expect.
Yeah, it's nice that each shape is rotating on a slightly different plane, yet the software is intuitive enough to really track the locations and align the POI to each lit component based on the new position within the measurement space or the defined field of view. Now that we've discussed the problems that we see in the market with previous methods and introduced the VIP as a new solution, let's review what this actually looks like in the software with basic demo, including the setup and analysis. So what you see here is the basic TrueTest UI. The first step is a training aspect of our solution, where what we want to do is define the search region, followed by the feature region, which collectively allows us to define our solutions area and save our model to the location of our choice. As you can see, we're defining the name and selecting the location to save the unique model. From there, we go back and we head on to step 2. Now that we've completed the first part of the sequence, we'll look at the analysis model of the lit icons and characterize their luminance and color components. Here you'll see the analysis results window where information like pattern match score, device rotation, luminance, and color of each icon are displayed. And all this information is logged and exportable. Chris, can you explain what's happening in this next section?
This is the same acquisition, but the part is rotated. Despite the rotation, the points of interest are correctly placed. And when looking at the analysis results window, as we will do right here, we see that the luminance and color measurements are the same, but the device rotation angle is found to be 22 degrees. A defect analysis is now performed. In this example, we see 2 defects in the airbag indicator and the daytime running lights. When the sequence is run, the software identifies the 2 defects based on predefined luminance and contrast, luminance, contrast, and size limits that are set in the software. We can then see in the analysis results that an image variation is found from the golden sample.
And this section is about pattern matching, and we'll see how the software will compare the trained model to the icon in the field of view whose dimensionality has changed. You can clearly see that the part is not the correct dimension when the contours of the model are overlaid on the current measurement. And in the analysis results, we'll see that the pattern matching score is very low, ultimately failing this part.
Thank you for that, Matt. So to summarize, what Radiant Vision Systems is offering is a single camera software solution that combines photometric analysis to measure light and color with defect detection to inspect icon quality. The software will perform measurements and pass and fail inspection based on user-defined points of interest, luminance thresholds, and CIE color region tolerances. And our solution eliminates the need to ensure perfect alignment between the system or fixture and components, ensuring fast, hassle-free measurement of multiple parts in succession. Now we can open up to questions and move into the Q&A portion of the webinar.
Thanks, Chris. We're going to start off by going through some of the questions that we received. So Chris, I'll filter some questions over you to start. The first question we have up here is, what does the registration use as a threshold to define the initial shape? Example, luminance, color, or other aspects?
Yeah, that's a great question. So the software does use a luminance threshold to define the registration, or the golden sample that we talked about in the video. However, there's a lot of flexibility with that thresholding, different image processing techniques and thresholding options. So it can really be tailored to what you're really trying to do, whether that's look for defects or different options. So there's a lot of flexibility for the user there. And then Matt, I have a question for you that has popped up. And the question is, can McAdam ellipses be used to define chromaticity tolerances? And if so, how would you do that?
Yeah, of course. So since we use a photometrically calibrated piece of equipment, and as long as we're using an imaging colorimeter, we could set chromaticity tolerances directly against the CIE space, whether we're looking at the 1931 or 1976 space, and we'd be able to define these using traditional McAdams ellipses, or we could have more robust options as traditional ellipses or polygons, rectangles, et cetera. So you can really define your specific requirement against your color criteria, whether it's in the automotive space and it's an SAE criteria, or it's coming from consumer electronics. That area can be defined, and then your points can be referenced against it. So, Chris, we'll just go back and forth, I guess, here. So how many characters or icons can be inspected at once?
Yeah, that's another great question. So there's a lot of different flexibility. It's going to come down to a couple of different factors, one of which is the resolution of the imager that we're using. And so Radiant Vision Systems offers a wide range up to really high resolution imagers, like a 29 megapixel and even a 43 megapixel. And then the other factor is going to be the size of the actual icon or character that you're using. So I don't necessarily have an exact answer to give, but I can say that with Radiant Vision System's high resolution, you can fit a lot of different icons, many icons in your field of view, and more importantly, you can really tailor it to what you need, and for typical applications like instrument clusters and some of the different icons and characters that we see, you'll certainly have enough resolution to measure all of those.
Right. So it'd be reasonable to say that, if there were 50 to 100 different lit icons in a field of view, as long as we had the appropriate resolution, we should be able to identify and characterize them, right?
That's absolutely right. That would be no problem. Okay. So here's another question. We talked a little bit about POIs and points of interest in the video. We didn't necessarily specify exactly how those are defined. So the question is, can you describe how POIs are defined?
Right. So POIs can be defined in a couple different ways. And what we were showing today was, of course, individual points of interest. So like circular areas that were plotted against the emitting icons. In one of the video slides, you can kind of see a contouring outline, which of course is considered a POI as well. So we have a defined points of interest window where basically you can set the criteria for thresholding, the size of the POIs, the placement, you can save that layout. And of course, you can have those layouts applied basically to the FOIs that we created, which was the very beginning of the video during the training segment. And then during the characterization and acquisition of the image, those parts are then physically applied with different pass-fail criteria, whether it be for luminance, color, sometimes contrast, etc.
Okay, thank you.
All right, so we touched a little bit on standards. So there's a question here on what are the MIL standards supported by this product?
Yeah, that's another good question. We did mention that in the video. So, what this will do was support testing according to the MIL DTL 7788, which is formerly an SAE standard. And then another standard that we can look at is the FMVSS 111 standard as well. Hopefully that answers that question.
Right. The FMVSS is not a MIL standard, but it's the one of the automotive standards. But yeah, I agree.
Exactly. Yeah.
Okay.
Yeah, sorry,
so let's see. Will the software confirm the amount of rotation is correct? So yeah, that might be a trickier question, but yeah, hopefully we can address it.
Yeah. So basically, when the software does its registration, one of the things is that it does find the rotation of the actual part, and that's actually one of the pass and fail criteria that you can do is based on the rotation, right? So if you have a part that has too high of a level of rotation, you can fail it just because of that. But the software does have the registration routine in the software does have a lot of flexibility to actually find the amount that something was rotated. So hopefully that answers. That's really what the question was getting at. And then Matt, I'll maybe find another question on here. So it asks about defects. And we talk a lot about defects in the video and throughout the webinar. The question is, are defects classified by type?
Right. So of course we talked about the ability to look at inclusions, exclusions, dimensionality, but basically what the software is doing is identifying those against different algorithms and not specifically classifying them as a unique defect. So we may find a variety of inclusions or exclusions, but those defects are not generally classified against a standard or even necessarily identified in the software as a line item that says, oh, this is an exclusion. It just identifies that there is a problem with the emitting icon or the laser etched component against the algorithms that have been selected and applied to the analysis.
Okay.
So of course they're all detected, but classification can be up for debate.
Mm-hmm.
All right. let's see. How many registrations can be stored in the software?
Yeah, so there isn't necessarily a limit for number of registrations, right? So you have a lot of flexibility to register the part and have different golden samples, and so you can perform a lot of registrations and set up a unique sequence specific to your application and your testing needs that have a bunch of different registrations. And as we showed in the video, for example, we save the registrations to a certain file path. So there isn't necessarily a limit, but that's, there's a lot of registrations that can be saved, and you can really do it specific to what you need.
Okay, great.
And then
I know that there's quite a few questions here about pricing. So we'll reach out to all the individuals asking about pricing directly, and we'll talk about the specific applications, because as we mentioned throughout the webinar, we create imaging photometers and colorimeters. So based on the technology or the resolution, the price would be dependent towards the application. So we'll be happy to reach out to everyone individually about those questions. Sorry, Chris, do you want to ask me another question?
No, that's a great point. Thank you for pointing that out. The question I have was going to be about cycle time. What are the typical cycle times for such, for this type of inspection?
Yeah, so of course, given that we're using metrology-based equipment, we have calibrated filters inside of our devices. So the cycle time is dependent on basically the light that is emitting from the component. But generally speaking, if we were looking at, let's say, a medical device that was, outputting a luminance value somewhere around, 50 to 100 candela per meter squared, you'd be at an acquisition process in the low millisecond range, somewhere around maybe 50 to 250 milliseconds. And then, of course, you have processing time. Your processing time is actually quite quick. So we can run multiple algorithms against the same acquired image. So if we wanted to look for POI placements, we wanted to look at rotation of device, we wanted to look if there was any inclusions or exclusions. What's nice about the Radiant software is we can run all those algorithms simultaneously against the acquired image, keeping cycle time really low. So depending on the amount of flexibility that you require during the acquisition process or the characterization process, that'll obviously stack against your tack time. But we've positioned ourselves with our imagers to be very competitive with traditional vision systems like machine vision when it comes to tack time analysis and process throughput. Okay, so I'll ask you maybe, I think we're running out of time here, but I'll ask you maybe one more question, Chris, and then for the questions that we didn't get to, we'll reach out to everyone individually as well. So, okay. There's actually quite a few here still. So I apologize that we're not able to get to everyone's questions. There is one about the ability to measure radiance, like a spectrometer. Do we have that capability?
Yeah, another great question. Obviously in this, we talked a lot about light in the visible spectrum. And that's, moving along with Radiant's filters that we have in our camera, we also do have the option to include essentially, which is going to be a clear filter that opens up our sensor to the full sensitivity or more wavelengths outside of just the visible spectrum. So we can look at measuring, in the near UV space as well as into the IR, which is certainly a new interesting application, and especially in a lot of cases with the military is an interesting application. So we do have the ability to measure radiance outside of the visible spectrum, specifically comparing to a spectroradiometer, because that was included in the question as well. We can, essentially our system is a CCD-based imager, so we certainly calibrate with a spectroradiometer. We have the option to calibrate with the spectroradiometer to scale our values according to that reference device. So we're just providing the radiance, not the actual spectrum of the source, but we certainly can measure accurately according to that reference device.
Okay, so I did say we were going to wrap, but there are just really a lot of good questions. So I'm going to ask a couple more to you, Chris. I'm just going to kind of rapid fire them off to you rather than going back and forth. So there's a great question here about your test piece does not need to be backlit, does it? For example, can a projected image be analyzed for color and accuracy?
So absolutely. You know, we really talked in the scope of backlits within this, but that isn't to say that we can't analyze projections in different illuminated cases, right, or different illuminated systems. We can look at the color and the illuminance of projections onto a wall or projections onto some sort of plane. That's really within the scope of our systems, and our software is able to adapt to that. So that's a great question, and absolutely this is within that scope.
Okay, I'm going to ask you two more. So what is the minimum letter size to measure with 2 megapixel lens? When they say lens, I'm sure they mean sensor. Or what is the relation between letter size and megapixels? So I think we're basically talking about how many pixels per character do we need for proper registration and analysis? That would be my understanding of the question.
I would think of the same thing. And, you know, because I talked earlier, I think in answering one of the questions about resolution and size, and when we're looking at characters, what we're really shooting for is about 10 CCD pixels across the smallest character for accurate and repeatable measurements, just to make sure that we're getting enough signal across enough sensor pixels on the imager to really accurately characterize that. So you could imagine, you know, something like a smaller resolution, 2 megapixel, you can still get a decent amount of characters in the field of view. And then with the high resolution imagers, you can measure a lot of different samples or many different samples, and you can measure very small samples as well. So, you know, shooting for the minimum CCD pixels, we're looking at about 10 CCD pixels across each area that we want to analyze the luminance and the color.
Okay, great. All right, so I will ask the last question then. Can the camera compare the golden sample with defined tolerances? So sort of like a pass-fail.
Yeah, absolutely. That's a great question. So we can set pass and fail criteria, a couple of different pass and fail criteria, just based on the registration alone. That's when we got a little bit into the pattern matching that we showed in the software demo. But you know, we can pass and fail based on how well the part is registered to the original part. So, you know, if we wanted to look at, you know, if it's a larger part, if the part that we're currently measuring is larger or is a different shape or a different contour, then we can pass and fail on that. That would be kind of passing and failing on the initial registration. Beyond that, for just luminance and color, within points of interest tools and different analysis tools, we have a lot of flexibility for pass-fail based on the luminance and the color as well. So there's a lot of flexibility in the software for pass and fail criteria and luminance, or on both luminance and color and pattern matching. Hopefully that answers that question.
Yeah, okay. All right, well, again, thank you everyone who attended. We actually exceeded our attendee capacity, so we will be reaching out to those who weren't able to join. And marketing will be sending a link to everyone if you wanted to share this information with any of your colleagues who are not able to attend today. Again, we appreciate everyone's time, and we will follow up with those who have outstanding questions. Thanks, and have a great Thursday.